Hey everyone, today we are going to solve LeetCode problem number 42, trapping rainwater. It's a very important question and marked as hard, but don't worry, we'll make it easy. And it has been asked in a lot of companies, as you can see, and it means that it's a pretty standard problem. So in this question, we are asked that we are given an elevation map and we have to give the trapped rainwater as an answer. You can assume that you have 2D ground 2D plane, and these are the towers, or you can say buildings. And after an infinite amount of rain, we have to tell like how much amount of water we can store. So let's say if there are two towers like this, how much amount of rain we are going to trap in between these two, the common portion among these two. Or maybe if we see in terms of its height, the minimum of these two at this point in the center. The minimum of the tower on the right side and the left side is going to be the height of the water. Let's say these towers are something like this. One tower, second tower, third tower. Can we store any amount of water in this? No. But if I introduce another tower here, and if after a certain amount of time or certain amount of rain, how much amount of water we are going to trap? We will be trapping this much amount of water because this is the common among these two. Okay, let me give you one more example. Let's say these are the towers 1 and 2, and there is no tower, and this one. Now, like if we straightforwardly draw, we will be trapping this much amount of water. Here what we are seeing is that the first building and the second and the last building is not contributing to any like is not trapping any rainwater. Why? Because on this building there might be possibility that on the right side there can be some wall which can hold some water, but on the left side we have a plain ground. It means a height of zero, or you can say in no building on the left side, so there is no support on the left side. So for this building we can use this support, but on the use this support, but on the right side there is no support. It means it's not going to store trap any water. Okay, let's see for another example. If all the tower are the same size, no, we are not going to trap any water. So what I got to know that to trap any water, let's say on this plane, if this building has to trap any water, there should be some kind of support on the left side and some support on the right side. Let's say on the after two towers we have this tower, and after three towers we have this tower. On the right side we have this biggest support. So what is the amount of rain we are going to store to this building? On the left side we are saying that this is the tallest building, and on the right side I am saying that this is the tallest building. So among these two we can have water. So how much water did this building store? That is the amount of support on the left side and the right side, and the intersection of those support. That is the tallest building on the left side, tallest building on the right side, and minimum of those two is going to be the height of the water. Okay, now let's try to come to this example. Here, if I write the numbers, this is of 0 height, 1 height, 0 height again, 2 height, 1 height, 0 height, 1, 3, 2, 1, 2, 1. These are the height of this tower, and we have to return the amount of rain water being trapped between these two. You can pick any one of the tower. Let's say we are picking this one. On this, the tallest building on the left side is this one, and tallest building on the right side is this one. So these two buildings will contribute to the rainwater trapping. because there is infinite amount of rain. We don't have to worry about the quantity of water, and we just have to trap as much as we can. So this is the amount of water we can trap. That is the intersection of this height and this height. Okay, now I think we got our idea for our brute force. That is, at every step, if we have to trap some kind of water, we have to know the highest or tallest building on the left side and tallest building on the right side. Okay, even if I give you a smaller example, let's say the example is something like 4, 2, 0, 3, 2, 5. If I draw this, let's say this is 4, so this is going to be 2, this is 0, this is 3, this is 2 again, and this is 5. We can easily see that this is 3, this is 4, so 4 and 5 will be contributing to the rainwater trapping, and this much area will be filled with the water. So if I try to come with our brute force approach, so for this tower of height 4, on the right side we have a tower of height 5, and on the left side we have a tower of height 0. It means there is no support on the 0, so this tower is have going to trap no water. For this tower of height 2, how much it can trap? On the left side, the tallest building is 4. On the right side, among all the buildings, the tallest building is 5. So the minimum of 4 and 5, the intersection, which is 4. It means the water can go till 4 height, and this is already 2. So 4 minus 2 is equal to 2. 2 unit of water we can hold. This is a ground, no building. So it's again 4, because on the left side we have 4, on the right side we have 5. And here we can see that over all the buildings on the right side we have 5, which is the tallest building. There is no tallest building on the right side of it. Okay, so what is our brute force in this case? That at every building we have to find the maximum height on the left side and the maximum height on the right side. So for every tower, how do you find the maximum height on the left side and right side? We can directly iterate over these towers, and at every step, let's say we are at index I equal to 2, so I will go till 0 till n minus 1. Okay, so let me just give you one example. Let's say this is the tower, and this whole range is having some towers. So for this tower, we will search for the left side and search on the right side. Let's say we on the left side we search k items, and total we were having n items. So how many items we search from the right side? N minus k. In total, how many items we searched at this index? N minus k plus k, which is n. It means that every value of I, we are searching n items again to figure out what is the leftmost height, what is the maximum height on the left side, and what is the maximum height on the right side. So I value will go from 0 to n minus 1. So it is going to be n into n time. Okay. So what I'm going to say is that my brute force is going to work something like this. At every index, I will search for the maximum height on the left side and the maximum height on the right side. And then I will take the intersection. How I'm going to take the intersection? The minimum of those two is going to be the common height, right? And that is going to be the amount of height of the water. At till this height the water can go, and that height we can subtract the height of tower from that height to know the height of actual water level. So what we did in our brute force, that every value of I equal to 0 to n minus 1, we search on the left side and we search on the right side for the maximum height on the left side, maximum height on the right side. And then we took the minimum of maximum height on the left side, maximum height on the right side. So this is the tower. Tower height plus water height, tower plus water is equal to this m value, minimum height. So what is the height of water? Water is equal to maximum minus tower, and the width is 1 unit. So we can easily calculate the amount of water. But here, what is the time complexity and space complexity? Time complexity we have already discussed, that every n element we are searching n more elements to know the maximum height on both sides. So the time complexity is going to be order of n square. And what is the space complexity? Space complexity, here we are not utilizing any space that we can consider as a constant space. We are only tracking some variables to store maximum height on the left side and right side. Okay, but we have to optimize this solution further because it's a quadratic time complexity. And what we encountered is that what we have to know here, the maximum height on the left side, the maximum height on the right side. As we have to know the maximum height so far on the left side, why don't we just keep on tracking the maximum height? Right? If we keep on tracking the maximum height, anyway we have to track the right side. Okay, but let's say if I take an array of left height, array of right height. So this array is going to store the maximum height on the left side, and this array is going to store maximum height on the right side. So how do we calculate these two array? Let's say we iterate over this input array and we keep on capturing the maximum height we have encountered so far. For the first tower, maximum height is 0. For the second tower, maximum height is 4. And for the all subsequent towers, maximum height on the left side is 4, 4, 4. Yeah, everyone is having 4 on the left side. Okay, and what about the maximum height on the right side? For this tower, the right side is 0. For this tower, right side is 5. For this tower, it is 5. This tower, it is 5. So it's something like this. 0, like this. 5, 5, 5, 5, 5. Maximum height on the left side, maximum height on the right side. So for every index, we know in advance what is the maximum tower on the left side and what is the maximum height tower on the right side. So we can easily calculate our result in O1 time at every index. What is the time taken to calculate these two arrays? Order of n time for each. So order of n time to calculate this array, order of n time to calculate this array, and order of n time to do the processing. So in total, it is going to be order of n time for this solution. And what is the space here? Space is also going to be in order of n because we are taking two arrays. Got it? Now this is a better approach. We discussed our brute force, which was doing the solution in O n square time, and now we are able to achieve the solution in order of n time. Now, as it is a hard question, the interviewer can ask you a follow-up question to do it without using this extra space. You have to eliminate this space. Okay, so how you are going to eliminate this space? In this example, you must have noticed that for every tower, the maximum height on the right side is of this tower, right? So if we already know the maximum height on the right side, then we can easily calculate the maximum height on the left side while iterating through left to right. Okay, so let's say if someone drop the problem, break the problem, and tell you something like that you have this numbers, and on the right side you have infinite amount of tower. If there is infinite amount of tower, we just have to worry about the left height. Let's say if on this example you see that this is the biggest height, this is the tallest tower, it means that no amount of water is going to be stored over it, because this is the tallest and there is no support on the left side and the right side. So if we break the problem into two half, let's say this is the one half and this is the second half, and if we ignore the second half, the first half will something look like the second example, this one. It means that at every step we already know the maximum height on the right side, and the maximum height on the left side we can calculate while iterating through left to right. Okay, so my ask is to just solve this amount of problem statement, and this we can solve later on, because this problem statement is breakable on this tallest tower, because no amount of water can be stored here. So maximum amount of height on the left side for this is 0, for this is 1, for this is 1, for this is 2, 2, 2, 2, something like this. So while doing the iteration from left to right, we are storing this value, and this value we already know. So we can do it in a order of n time, but this time without using any extra space. It means without capturing those maximum height on the left side in an array explicitly. But you must be asking me that how this is calculated. This we can directly calculate by doing the one iteration. So initially do one iteration and capture maximum height in the maximum height in the whole street or whole space. So the tallest tower. The tallest tower we can directly calculate by doing one iteration. And after that, we can break our problem into this half and this half. And this half is also something like this. This height is already fixed. And this height we can say that maximum height on the left side and the maximum height on the right side we can calculate by doing one iteration from right to left. Okay. So I hope the concept is clear to you. So initially we did n square solution, order of n square solution, where at every tower, let's say this is the tower, this is the tower, at every tower we were capturing the maximum tower on the left side, maximum tower on the right side, and then we're finding like what is the support we will get to store the water. Okay, but this is an n square solution, or we have to optimize it. To optimize it further, we pre-computed the maximum height on the left side and the maximum height on the right side. So we pre-computed these values to these two arrays. In this way, we like we were able to solve the problem in on time, but we were using on space. But later on, we did a very great observation that the tallest tower is not going to store anything. So this tallest tower, if we fix this tower, this problem and this problem is similar, just opposite to each other. It means that one side is already fixed and the other side we can calculate while doing the iteration. That is, we are eliminating these two arrays. So we are eliminating our space, and space is going to be order of 1. Let me give you the solution, or let me show you the solution for the approach where I'm solving this problem in the on time. One is with on space and one is without any space. So here if you look at the code, I have taken two array, maximum height on the left side, maximum height on the right side, and I have pre-computed these two arrays, and after computing these two arrays at every index I know the maximum height on the left side and the maximum height on the right side, and I will get the intersection of those math.min. and I will just deduct the actual tower height. It means this is the height of water, and that is going to be added to the sum, and we got the answer. And in the second approach, what we will do is, firstly we will capture the maximum height. Here in this solution, what I did is, firstly I captured the maximum height, along with that the maximum height index. That is, if the towers are something like this, this is the maximum tower, so there is no amount of water over it. So we can break this problem into two halves, first half and second half. So first of all we have to capture the maximum height, or maybe its index. Then what we'll do is, we'll go from left to here and then right to here while solving our solution. So the maximum height we have captured, and now what we are going to do is, we will be going from left to right. While iterating from left to right, we will keep on capturing the maximum height on the left side. Okay, using this maximum height so far. And the same thing we are going to do on the right side. From right to left, we'll keep on capturing maximum height so far in our iteration, and maximum, and that is going to be the maximum height on the right side. And the maximum height on the left side we already know. So we can easily compute the intersection of those two tall tower on the right and left side. Okay, I'm going to attach the solution in the description, and I hope you understood the problem. If you have any doubt, you can comment down below. We will be discussing further in the comment section. Okay, thank you guys. Bye bye.